Now we'll discuss the interference in thin films. Okay, look at this one. So what is the topic we have picked up? Interference in thin film. So usually where do we see this interference in thin film? So when you go to during rainy season, so at petrol bunk, so some oil or petrol will be spilled on the floor of the petrol bunk. And since it rained and some oil spilled, we can see some sort of colors, no? Especially during when if the sunlight is incident or in the night, we see different colors. Any reason for that? It is due to interference due to thin films. Or another thing, soap bubbles. Why do they appear in different colors? Soap bubbles, you might have noticed, no? They'll have some different colors here. What is the reason for that? It is due to interference in thin films. Or what you can do is like you take some in a some container, put water, sprinkle some 2-3 kerosene drops, and try to view it from certain angle. You can see some sort of like a different colors. The film, the surface of water will appear different colors. Any reason for that? Interference due to thin film. This is what happens here. You can try these things at home. Hmm? Okay, now let's proceed here. So a broad source, not like a ray of light. It is not a ray of light. So we are just assuming like a broad source. Broad source means like a sunlight falling on certain surface of water or the light coming from tube light. They are the examples of a broad source. So when the broad source is incident on a certain film, this one. So there's the incident ray. It is incident at an angle theta. Then we know like it will encounter a boundary because this is the air and this is the film of refractive index mu. It is given. Then a part of energy will be reflected. Got it? A part of energy will be transmitted or refracted. Better you see. So once again, put it. There's the incident ray. A part of energy will be reflected. Got it? And a part of energy will be refracted. This is one property of a medium. Then, and look at this. The ray, incident ray is in air, and what about the reflected? The reflected ray is reflected by denser medium. So what is this medium? Air refractive index is almost equal to 1. What about this film is having mu greater than 1? So which will be denser, which will be rarer? The film will be denser and the air will be rarer medium. This will be a denser medium and this particular air will be, let me write it here. This air will be a rarer medium. Okay, got it. Now, let me share it. So what is this? This film I'm giving yellow color, so that you can notice the difference between the air and this one. This yellow color rectangular block is what? The film. It can be oil film, or it can be some kerosene drops on the water, or some petrol drops on the surface of a water. Any of the condition, or on a glass plate, you sprinkle some sort of chemical. So some thin film will be formed here. So what is the thickness of the film? Let it be T. Okay, I think okay, this is completed. Let's take the overall condition. Yeah, I think okay. Now I think things are a little bit very clear for you. Let me take the highlighter. No, there's incident light. This reflected light by whom it is reflected by denser medium, and we know when a wave reflected by denser medium should undergo phase change of pi radian. Got it now? So what was the phase of the incident is 0. After theta is the incident angle. 0 is the phase angle of incident. After reflection, the reflected ray will undergo phase change of pi radian. What about the refracted ray? We know due to transmission, no phase change will occur. So what is the phase of the refracted ray will be zero only. Then again, a part of ray will be reflected, part will be transmitted. How refracted? The ray moves from denser to rarer, so it will bend away from normal. And then due to refraction, there won't be phase change. So what is the phase of the ray 6 will be zero. What about the phase of the ray 4? Ray 4 is what? Reflected by a rarer medium. This is a rarer medium. So what is the phase angle of that? Will be zero. Okay, now again it will encounter a boundary. A part of ray will be reflected. I'm not showing it. Later on I'll come. And a part will be transmitted. The ray 5 will be transmitted. Now you see that one. Ray 3 is what? Reflected by a upper surface of the film, or reflected by denser medium, phase change of pyridine. What about ray 5? It will be reflected by the lower part of the film. And this is rare, rarer, this is denser. So will there be any phase change for this? No. And due to transmission, no phase change. So what is the phase angle of the ray 5? Will be zero. Of course, it will have some path difference. Due to reflection, there won't be any phase change. Okay, now let's take the superposition of 3 and 5. Practically, what will happen? 3 and 5 will be parallel. If two rays parallel, can they undergo superposition? Not possible. But sir, how you are showing that? But you are not showing will not be parallel. But the I is present here. The here I wrote a comment also will not be parallel. Okay, let's go back to the some basic optics what we know. According to the optics, ray optics we know it, no refraction. Okay, let me take help of that. The ray is incident here will undergo refraction. This is a ray 1. This is a ray 3. This is a ray 2. This is a ray 4. What we know, these two must be parallel. No. I think they appear parallel. Okay, let me show clearly. They are parallel. This is a ray 5. I think that this is what happens. Again, further, this will get reflected. This is a ray 6, ray 7, this is a ray 8. Okay, try to make notice here. So here, these two are parallel. But I'm writing not parallel. What is this? If this is a smooth, perfect. Ideal case, if it were the film were perfectly smooth, okay, then the 3 and 5 in this diagram, look here in this diagram, then the 3 and 5 what happened will be definitely will be parallel. But practically you look at any film will not be smooth, will be rough. There'll be some deformations. So due to that deformation, so you look at any surface will not be perfectly smooth. There'll be some deformation. Perfectly smooth, 3 and 5 will be parallel and no question of superposition. Why do they undergo superposition? They'll not meet. But 3 and 5 will undergo superposition. For them to undergo superposition, they're not more parallel. For them not to be parallel, the surface of film will be rough, will have some ups and downs, or what you can say. So because of this, what the 3 and 5 will not be parallel. Okay, got the idea now? So thin film, the interference in thin films will not be observed if the surface is smooth. If the surface of a film is smooth, okay, no question of anything. Okay, this is very important. Okay, this ideal case, what we're discussing, this ideal one. Practically, this what happens. The surface, in fact, will be rough. And because of that, 3 and 5 will never be parallel. So they'll undergo superposition. Okay, let's discuss about the eye which is present when these rays undergo superposition, and that the resultant wave enters into eye. The eye is going to see the film. Some colors will be missing. Some colors will not be some colors will be appearing, some colors will be missing. Means in fact, this incident ray is a white light. Then what we should see? I should see VIBGYOR. I should see on the film the VIBGYOR. But practically what happens is some wavelengths are missing, some wavelengths are not missing. Why some wavelengths are dominant? Why some colors are dominant? And why some colors are not dominant or not visible? Some wavelength will undergo constructive interference. Some wavelength will undergo destructive interference. Those wavelengths undergo destructive interference. So no question of any light by them entering into eye. Those which will undergo constructive interference, by them will enter into eye, and the eye is able to visualize that particular color film. Okay, let's get into the mathematics here. So let's discuss the path difference between the net path difference between rays 3 and 5. There's a ray 3 and the ray 5. We'll discuss the path difference between these two rays. Okay, now compared to ray 3, the ray 5 has to cover this much of additional path, where in film of refractiveness mu. So what is the optical path length? Mu t, 2 mu t. So let for small angle of incidence. So if theta is very small, then the angle of refraction will also be very small. So in general, what happens? We can just say like almost like for normal incidence. Then what is the additional path? The ray 5 will cover compared to ray 3. There's a path 2t. Optical path length of that 2 mu t minus no. What is the additional path? The ray 5 will cover before undergoing superposition ray 3 t plus t 2t, where in slab or film of refractiveness mu. So what is the optical path length? Will become 2 mu t. Now why this lambda by 2? The ray 3 got reflected by a denser medium, so it is having a phase change of pi radian. It is having a 0 phase due to reflection. So what is the path difference between ray 3 and the ray 5? That should be equal to 2 mu t minus lambda by 2. No, I want constructive interference. For constructive interference, what is the delta x? Should be equal to n lambda. So here I'll write it n lambda. So n lambda equal to 2 mu t minus lambda by 2. Let me solve for this equation. So I'll take the lambda by 2 on left LHS. 2n plus 1 lambda by 2 is equal to 2 mu t. I took the lambda outside. It will become 2n plus 1 lambda by 2, where n equal to n will start with 0, 1, 2, 3, 4. I'll get the thickness. If the thickness of film corresponds for those values is that particular wavelength, or if the wavelength satisfies that particular equation, then we can see that only that particular wavelength will undergo constructive interference. So what is the meaning of this? Okay, let me explore that equation. So what is it? Like a lambda should become equal to 4 mu t by 2n plus 1. Those wavelengths which will satisfy this equation, put n equal to 0, 1, 2, 3, 4, like that. Those wavelengths which will satisfy this equation will undergo constructive. Then those wavelengths which will satisfy this equation, so like a lambda is equal to 2 mu t by n. And n should not be 0. N will start with 1, 2, 3, 4. Put n equal to 1, 2, 3, 4. Then what we can say, a condition for destructive interference, what we can notice here. Means which wavelength will undergo constructive or destructive. Means which wavelengths will be dominant, which will be visible, which will not be visible. Those wavelengths which will satisfy this equation, they'll undergo destructive interference. Those which will undergo this, satisfy this equation, they'll undergo constructive interference. And I'll put a boundary like this. Fine. Like this, we can see why the different colors and why some wavelengths are dominant at this. Why the eye will notice that some wavelengths are dominant. Those wavelengths which will satisfy this equation 4 mu t 2n plus 1 lambda by 2 constructive interference, and the wavelengths will be dominant. Those wavelengths which will satisfy this equation, they'll undergo destructive, and we don't see any light entering into the eye due to that particular thing. So that's why some wavelengths will be missing here. The missing in the sense, what happened, what you should say, they'll undergo destructive interference. Okay, got this. So there's overall the theoretical idea of interference in thin films. Now we'll look at some conditions. Let me bring the pointer. If thickness of film is very small compared to wavelength, the reflected rays 3 and 5 undergo destructive interference. Because if thickness is very small, then they'll undergo destructive interference only. Then the film will appear dark. They're the one primary condition. What is telling, if thickness of film is very small compared to wavelength, the reflected rays 3 and 5. Because what is the reason for that? Because the 3 and 5 okay, I think it's complete the condition is visible. What is the phase angle between 3 and 5? What is the phase difference between them? Phase difference between them, pi radian. And if thickness is very small, so almost this optical path length you can neglect. So what is the net phase difference will become? Only pi. If the phase difference is pi, then they'll undergo destructive interference. And this eye, what it will notice? It will just say that the film is dark. Though light is incident on the film, but still the film will appear dark. That's what the meaning, the film will appear dark, is what he's saying. No, practically what happens is there's a theoretical thing. Practically what will happen is like the amplitude of the ray 3 and ray 5 will never be equal. The reason for that, suppose say here, if a light comes with an intensity of say like 100 watt, a part will be reflected, a part will be transmitted. Again, the light will be, a part will be transmitted, part will be reflected. Again, look at this one. A part of light will be reflected, part will be transmitted. What do you expect the amplitude of R1, R2 will be different? Okay, no, I think you are finding it a little bit difficult. Okay, let me explore with some values. It'll be much easier for you. Suppose this comes with an like a intensity, so like or the power, or whatever you can take this one. Let it come with 10 watt. 4 watt of will be reflected, and the remaining 6 watt will be transmitted. Again here, again some select 3 watt will be transmitted, 3 watt will be reflected. So here what will happen is like in the 3 watt, the 2 watt will be transmitted, and the remaining 1 watt will be reflected. Look at the now amplitude of these two. The power of these two are different, then amplitude will be different. So when do complete dark will come? When two waves. So what is the formula for I minimum? If I1 equal to I2, then I minimum will be 0. If I1 not equal to I2, then I minimum will be non-zero. So what is the amplitude of R1 and R2? What is the amplitude of this R1 and R2? The reflected rays R1, R2 will be different, and therefore in fact R1 greater than R2. Similarly, what if the amplitude of R3 will be still more lower value? So when superposition of R1, R2 occurs, so do we get really completely dark? No, constructive, though destructive interference occurs, but the intensity alpha will not be 0, will be non-zero. So therefore, the film appearing completely dark, practically not possible. Completely dark is not possible. There's the basic idea. So very important. So this is thin film. Thickness film is negligible. When thickness of film is negligible, in that case, what happens? The film will not appear dark. Theoretically, I said earlier, there's a statement, but so there's a reason what we can give. Next, after this condition, what happens if the film is thick? The third condition. Thick in the sense like I'll pour oil in a container. Let me pour some oil in a container. Then let me make a white light incident on it. Then this is the eye. The human eye, not it's like a human eye. So let the human eye do I see any interference here, or do I see any colors on the screen? The answer is no. Any reason for that? Here also what happened? The light which is coming, a part of light. Let me bring the pointer. So here also what will happen? A part of light which is incident, a part will be reflected, a part will be transmitted. Again, we'll get it here. So like this, we'll get it. Here the interference of the two reflected rays, R1, R2 will take place. Don't say that no R1, R2. There'll be reflected rays. And again, what happens? Some rays will undergo constructive interference, some wavelength will undergo constructive interference, some waves will undergo destructive interference. Because of the film very thick, the bright regions and dark regions will be so close to each other that so they overlap. If they overlap, what we see that one, we don't see any different colors. The film is very thin. That's why you just pour oil in a container and keep it nearby tube light, LED bulb or white source of light. Do you see any colors? The surface of the oil appearing any colorful? Nothing. Just like a plain, what was the color of oil, it will appear that much only. The reason why we don't see different colors like a soap bubble, how we see the different colors, no, glistening one, glowing one. We don't see such colorful. Will not be colorful. We don't see different colors. So here, what is the comment? Not colorful. Any reason for that? Because again, everything, there'll be constructive interference. Some wavelength will undergo constructive interference. Some wavelength means it happened here. These two will undergo constructive. Some wavelength, they come here. They'll undergo destructive. The bands, the maximum and minimum bands, or the interference bands which are having maximum minimum intensity, they overlap, and all together we don't see any like a distinct colors. So that's why we just like we don't see different colors. A good example, you fill up water in a bucket and let the keep it in sunlight. Do you see any colors on the surface of water? Nothing. The reason for that, because the water layer, what happen, will be like a thick film it will become. Instead, you pour some oil drops on the water surface of water. Then the oil drops will become thin film, and you can notice the different colors. Okay, got this one? There's a thing. Now the fourth condition is what? One more condition, let me introduce. The fourth condition is like the source light must be broad. We should not discuss this interference due to thin films due to ray of light. No, sunlight will be incident on a film. Then we can see this particular interference phenomena. If you just send a ray, take laser beam and focus onto the surface of thin film, yes, we don't see that particular like a film appearing colorful. So the source of light incident on the film, on thin film, must be broad. The source of light. broad beam of light. What do you mean by this? Means like, sir, not understanding. Not understanding means if you take there's a film, it should be like a beam of light. A good example, this is sunlight. Kerosene oil drops. This is water. Not one ray of light. It should be discussed for broad source of light. Okay, now so the overall. Okay, let's. So what we discussed, the interference in thin films. And this was the mathematics is what we had. Hope I think everyone is able to understand things very clearly. Okay, one primary thing. What is there's a film? What is the layer behind this film? Air only. We discussed the problem like this air. What is the layer above this is also air. Let's slightly change this condition. There are two layers are there. So there's a layer 1 and next another layer, layer 2. Able to notice there's a layer 2 is having a thickness T2. Next another layer 1 is having a thickness T1, refractiveness mu1. So let me put a condition mu2 greater than mu1. So the incident ray will come, will strike first the interface between A and the first film. Then a part of ray will be reflected, a part will be refracted. The reflected will undergo phase change of pi radian because reflected by denser medium. Then at second interface, what is second interface? The second interface, this one between mu1 and mu2. You can see here now, mu1 and mu2. Here, what is the thing? This is a denser, this is a rarer. At first boundary, the air was rarer and the layer 1 was denser with respect to that. So therefore, the reflected, the ray 3 will undergo phase change of pi radian. No, the interface between films. So the ray moves from rare to denser. So the reflected ray will undergo phase change of pi radian. The reflected light will undergo phase change of pi radian. And the refracted ray has no phase change. Now, again, this ray, when it goes here, a part of ray will be transmitted and a part will be reflected. Since what is the phase angle of this? Pi, the ray 4 is having phase angle phi. So due to transmission, due to refraction, no phase change. So this will be pi. The reflected light is reflected by rarer medium, phase angle pi. Are you getting some different situations? Are there? Try to notice that phase angle. Whenever a ray reflected by a denser medium, it should encounter a phase change of pi radian. The reflected light will gain a phase of pi radian. Now look at the superposition of 3 and 5. What is the phase angle between them? Pi radians. What is the phase difference between them? 0. Earlier it was pi radians. Now it is 0 phase angle. Okay, let's come for what is the path difference between the rays 3 and 5. The ray 5 open will cover a path of 2t in film of refractance mu1. So what is the optical path length? 2 mu t. I'll put once again. The ray 5 has to cover a path of how much? 2t. So what is the optical path length will become 2 mu t. Then what is the phase difference between them? 0 due to reflection. So net path difference is what? Will be 2 mu t. For constructive interference, the delta x, I'll write it as n lambda. I'll solve for n. What is n? N equal to 1, 2, 3. What should be the thickness? Yes, n lambda by 2 mu. Or what should be the wavelength which will undergo constructive interference? 2 mu t by n. For destructive interference, what should we write? delta x should be equal to 2n minus 1 lambda by 2. Okay, those wavelengths which will satisfy this equation they'll undergo constrictive interference. Those wavelengths which will satisfy this equation will undergo destructive interference. Okay, got this one? So why that some wavelength will undergo destructive interference, why certain wavelength will undergo constructive, it all depends upon this idea. So again, both are thin films. This is also thin film. So if there are more than one film is there, I think we have to be very alert. Is it mu2 greater than mu1 or mu2 less than mu1? If mu2 less than mu1, then again it is similar to the previous case what we discussed. So this is about the interference in thin films due to reflected light. Even the transmitted light also will undergo superposition, and we can discuss the similar ideas here also. Even the transmitted light also, for transmitted light also, we can discuss a similar condition. Let's discuss this. No. No. Let me start with, okay, let me take some other color. Now, what is the phase angle of this? 0. So there's a denser medium, mu, and there, let T be the thickness. Let me take some thin one pen. Okay, I think this will be better visibility. Yeah. Now, what is the phase angle of this incident ray? Let me call this as an incident ray. So the ray 3 is reflected by a denser medium, phase angle pi. Due to transmission, the refracted ray 2 will not undergo any phase change. So what we should write? 0. Then, so this is again air. So no phase change, 0, 0. What about here? This will be 0. Because due to transmission, no phase change. Again, this should be 0. Look at very clearly now. I'm superposition of 6 and 8. Superposition of rays 6 and 8. Please try to look at this right hand corner. This one. I'm not. Don't look at this diagram. Look at this. Look here. Or else I'll magnify it. What is there in this one? We have option, no? Hope you are able to see only this. No. So proportion of 6 and 8. What is the path difference? So how much the ray, this ray will cover a path, the ray 8 will cover additional path of how much? 2t. What is the optical path? 2 mu t. So therefore, for constructive interference, what is the condition? Path difference should be equal to 2 mu t, and this should be equal to n lambda, where n equal to 1, 2, 3, 4. This is for transmitted light. We are not discussing for 3 and 5. We are discussing for 6 and 8. Here is what? There's a transmitted light. Now, similarly for where n is equal to for destructive interference. Let me write destructive interference, then I'll write the equation for destructive interference. Path difference should be equal to 2n minus 1 lambda by 2 should be equal to 2 mu t, where n equal to 1, 2, and 3, 4. So it will be reverse what we see for constructive destructive interference. No, the conditions are little bit reverse. I think complete thing is visible. This section is totally different. Okay, this is about the basic idea of the interference in some thin films. Okay, after this, we'll go for the next, this one. We'll take the billet lens. Okay, we'll discuss the idea behind the billet's lens theory, that one. So first we'll have, what do you mean by that billet lens? So we'll start with this. So there's actually a lens, and this will be the optic axis. Now I'm going to cut the lens into the two equal